When ChatGPT answers a difficult question, writes a piece of code, or explains a complicated idea step by step, it can genuinely feel like there is someone thinking on the other side of the screen. It pauses, analyzes the problem, corrects itself, and sometimes even says things like, "Let me think about this carefully." But is AI actually thinking? Or is it simply producing a very convincing imitation of thought? This question sounds philosophical, but it is also one of the most important technical questions in artificial intelligence. Because if we want to understand what modern AI can do, where it fails, and whether it could eventually become more intelligent than us, we first need to understand what its reasoning ability really is and where that ability comes from. Let's start with something that often surprises people. A large language model is not originally trained to reason. At its core, it is trained to predict the next piece of text. If I write, "The capital of France is," the model predicts that the next word will probably be Paris. If I write 2 plus 2 equals, it predicts 4. During training, the model sees enormous amounts of text and repeatedly tries to guess what comes next. When it makes a bad prediction, its internal parameters are adjusted slightly. This process happens again and again across billions or even trillions of examples. That sounds almost too simple. How can predicting the next word possibly lead to coding, mathematics, planning, explanation, and logical reasoning? The answer is that language contains much more than vocabulary. Language contains patterns of thought. A textbook doesn't only contain facts, it contains explanations. A mathematical proof contains a sequence of logical steps. A programming discussion contains a problem, an attempted solution, an error, and a correction. A scientific paper contains evidence, hypotheses, comparisons, and conclusions. So when a model learns to predict language extremely well, it cannot rely only on memorizing which words commonly appear next to each other. To make accurate predictions across many different situations, it has to learn deeper structures hiding behind the text. It has to learn relationships between concepts. It has to learn that causes usually come before effects, that a conclusion should follow from evidence, that code must obey syntax, and that a mathematical answer often depends on several intermediate operations. The model is never explicitly told, "Build an internal representation of logic." But some kind of internal structure becomes useful because it improves prediction. This is where AI reasoning begins to emerge. Think about a chess player who studies millions of games. At first, the player may simply memorize common moves. But eventually, memorization is not enough. The player begins to recognize deeper patterns, weak squares, exposed kings, tactical threats, and long-term positional advantages. A language model goes through something similar, although on a much larger scale and with a very different architecture. It begins with surface-level language patterns, but as the model grows and sees more data, it can develop internal representations of objects, relationships, intentions, and procedures. This does not mean there is a tiny human-like mind inside the machine. It means the network has learned mathematical structures that allow it to process information in ways that sometimes resemble reasoning. One of the main technologies making this possible is the transformer architecture. When a model reads a sentence, it does not process every word in isolation. It uses a mechanism called attention to examine how different parts of the text relate to one another. For example, in the sentence, "The robot dropped the glass because it was too slippery," the model needs to determine what it refers to. Is the robot slippery, or is the glass slippery? Attention allows the model to connect relevant pieces of information, even when they are separated by many words. In a more complex problem, the same mechanism can help the model connect assumptions, intermediate steps, and conclusions. Different layers of the network gradually transform the input. Some patterns may track grammar, others may identify entities, relationships, code structures, or numerical operations. By the time the model generates an answer, the original words have been converted into a large network of internal numerical representations, and those representations are not fixed dictionary definitions. Their meaning changes depending on context. The word bank means something different in a discussion about money than it does in a sentence about a river. The model learns this difference not because someone manually programmed two definitions into it, but because the surrounding patterns are different. Reasoning works in a similar way. The model learns that the correct next step depends on the structure of the problem currently in front of it. But there is another important part of the story. Modern AI models do not get all of their reasoning ability from basic next word training. After the initial training stage, models are usually refined using examples of useful answers, human feedback, automated feedback, and carefully designed reasoning tasks. Suppose a model gives the correct answer to a math problem, but provides a completely broken explanation. During additional training, that answer can be rated poorly. A clearer and more logically consistent response can be rated more highly. Over time, the model becomes more likely to produce answers that appear organized, relevant, and logically connected. Some models are also trained using problems where the quality of the reasoning process matters, not only the final answer. They may be rewarded for finding correct intermediate steps, checking their work, using tools properly, or changing strategy when the first approach fails. This is one reason newer reasoning models can appear much more deliberate than ordinary chatbots. Instead of immediately producing the first plausible response, they can spend more computation exploring possible solutions. They may break a problem into smaller parts, test different approaches, and compare possible answers before responding. In simple terms, more thinking time can sometimes produce better results. Humans do something similar. If I ask you what color grass usually is, you probably answer immediately. But if I give you a complicated logic puzzle, you slow down. You hold several possibilities in your mind, eliminate contradictions, and maybe write down some notes. AI systems can also benefit from using more computational steps on harder problems. But we need to be careful with the word thinking. When a human thinks, there is usually a subjective experience involved. We feel uncertainty. We have goals, emotions, memories, sensations, and a sense of being present. We do not currently have good evidence that a language model experiences any of those things. When an AI says, "I'm confused," that sentence does not prove the AI feels confusion. It may simply have learned that this is an appropriate phrase to use when the information is inconsistent. In the same way, when a character in a novel says, "I'm afraid," the sentence represents fear, but the ink on the page is not afraid. So AI can perform operations that function like reasoning without necessarily possessing consciousness. This distinction is extremely important. Reasoning is something we can evaluate from behavior. We can give a system a problem and see whether it reaches the correct conclusion. Consciousness is about subjective experience. That is much harder to measure, especially in a machine. An AI might become excellent at reasoning while still having no inner experience at all. Or perhaps future systems could develop something more complicated. At the moment, nobody has a reliable scientific test that can settle this question. There is also a major weakness in AI reasoning that reveals how different it is from human understanding. A model can produce a brilliant explanation in one moment and make a ridiculous mistake in the next. It might solve an advanced programming problem, but fail to count the letters in a word. It might explain a scientific theory accurately and then confidently invent a research paper that does not exist. Why does this happen? Because the model is always generating the most plausible continuation based on its training, its current context, and the internal computations it performs. Plausibility and truth are often connected, but they are not the same thing. A false statement can sound extremely convincing. Humans also make mistakes, of course, but we are connected to the physical world in a way language models are not. We can look at an object, touch it, test it, and see what happens. A language model mainly learns from representations of the world created by humans. It reads descriptions of falling objects, but it has never physically dropped a glass. It reads about pain, hunger, distance, and time, but it does not experience these things the way we do. This can make its knowledge broad, but sometimes fragile. It may understand a concept well in familiar language patterns, but struggle when the same concept appears in an unusual form. That is why researchers are connecting AI models to tools, code execution systems, search engines, cameras, robots, and external memory. A calculator reduces arithmetic mistakes. A search tool helps verify current information. A code environment allows the model to test whether a program actually runs. A robot can receive feedback from the physical world. Once AI can act, observe the result, and adjust its plan, its reasoning becomes much more grounded. Imagine asking an AI to organize files on a computer. A basic language model might only describe the steps. An AI agent can actually open folders, inspect file names, move documents, notice an error, and try again. In that situation, reasoning is no longer just a sequence of words. It becomes part of a loop: observe, decide, act, check, and correct. This loop may be one of the most important directions in the development of artificial intelligence. So, does AI really think? My honest answer is that it depends on what we mean by thinking. If thinking means manipulating information, recognizing relationships, comparing possibilities, solving problems, and producing logical conclusions, then yes, modern AI can perform some genuine forms of reasoning. Those abilities are not necessarily fake just because they are produced by mathematics. Our own brains also operate through physical processes, even though the details are completely different. But if thinking means having self-awareness, feelings, personal intentions, and an inner experience of the world, we do not currently know that AI has any of those things. The safest conclusion is that AI reasoning is real as a capability, but it is not the same as human thought. Its reasoning comes from several sources working together: massive amounts of human-generated data, the pattern, learning ability of neural networks, the attention mechanism of transformers, additional training based on feedback, and extra computation used to explore difficult problems. What makes this so fascinating is that nobody manually wrote all of its reasoning rules. Engineers created the architecture and the training process, but many abilities emerge from the system learning at scale. And that may be the biggest lesson here. Intelligence might not require us to program every rule individually. Under the right conditions, complex reasoning can emerge from a system learning to predict, represent, and interact with the world. AI may not think exactly like us. It may not understand the world in the same way we do, but it has already shown that reasoning can exist in a form very different from the human mind. And as these systems gain better memory, stronger verification, more powerful tools, and greater access to the physical world, the line between predicting an answer and genuinely solving a problem is going to become increasingly difficult to see. The real question may no longer be whether AI thinks like a human. It may be whether human thinking is the only kind of thinking that deserves to be called thinking at all.